Looking at the topic of ultrasound, we are going to look at the piezoelectric transducer and receiver. We are also going to look at specific acoustic impedances and intensity reflection coefficients. Now, the diagram shown here is that of the piezoelectric transducer. It can also be used as a receiver. A piezoelectric transducer operates as both an ultrasound generator by applying a stimulating voltage of suitable frequency, thereby causing a crystal vibration and the emission of ultrasonic waves. It can also function as an ultrasound detector by detecting the piezoelectric voltage developed across the crystal when it is forced to vibrate by incoming ultrasonic waves. Opposite sides of the piezoelectric crystal are coated with silver to act as electrodes. So on the diagram, we have the piezoelectric crystal, which is this one here that you see. So it is coated both sides with silver so that it can act as an electrode. Okay, right there. When an alternating voltage is applied across the electrodes, it causes the crystal to vibrate. So the crystal starts to vibrate, and the vibrations are in the ultrasonic region. Remember that ultrasound is any sound that is above the upper hearing limit of a normal human being, that is above 20,000 hertz. So this crystal vibrates when you apply an alternating voltage. The crystal vibrates at a frequency that is in the ultrasonic region. Now, when this frequency of the applied voltage is equal to the natural frequency of vibration of the crystal, resonance occurs and the vibrations have maximum amplitude. The disc thickness determines its resonant frequency. The thicker the disc, the lower the frequency. The dimensions of the crystal can be such that the oscillations are in the ultrasonic range that is greater than 20,000 Hz, thus producing ultrasonic waves in the surrounding medium. The electrode nearest the patient is connected to earth for safety. So there we are. So that's nearest the patient. The other electrode is the active electrode or the live electrode, and it's connected via a coaxial cable to the source when it is used as a transmitter. So there you are right here. So that's the coaxial cable. Remember, in the topic of communication, we talked about coaxial cables. So we apply the alternating voltage across there, and then the crystal is made to vibrate. Clear, distinct echoes are obtained using short pulses. A typical pulse time period is of the order of microseconds. To generate such pulses, the vibrations must be damped as quickly as possible. Remember the topic on oscillations when we looked at damping. This is achieved by bonding a block of damping material to the back face of the crystal. The block is made of a suitable absorbing material such as araldite or other epoxy resin. This which damps the disc vibrations rapidly at the end of each pulse before the next pulse is obtained. This is also to prevent ultrasonic waves being created at the rear surface of the disc. So we make sure that we try and stop the vibrations soon after. Only those vibrations that we need are the ones that reach the patient. But the ones that develop at the back need to be damped so that we don't have any other ultrasonic waves. If this was not done, the ultrasonic waves from the two disc surfaces would cancel out each other and we end up not having anything. Remember, on interference. Specific acoustic impedance and intensity reflection coefficient. When an ultrasonic pulse enters the body, it is reflected from the boundary between different types of tissue. The ease with which an ultrasonic pulse can travel through a material depends on a property of the material called the specific acoustic impedance. Is given a symbol capital Z. The specific acoustic impedance is defined as the density of the material, rho, multiplied by the speed of sound in the material, that is C. So Z is equal to rho C. The units of specific acoustic impedance are kg per meter squared per second. And values for the acoustic impedance of some materials are given in the following table. So the acoustic impedance of air is about 429. Of water is 1.5 times 10 to the power of 6. Blood 1.59 times 10 to the power of 6. All the way down to quartz, which is 15.2 times 10 to the power of 6. The greater the difference between the acoustic impedances of two material media, that is at boundaries in the body, the greater the amount of reflection. Two materials with the same acoustic impedance would give no reflection, that is, all the ultrasound will be transmitted, in other words absorbed into the body, so there will be no reflection, while two with widely separated values would give much larger reflections. Right, so I'll give you an example. Say we have between water and blood, so you look, these are almost the same, so you've got to have a considerable amount of reflection, a considerable amount of absorption taking place there, and very little reflection takes place. So the greater the difference, like from air to blood, so that's a great difference there between the two. Therefore, more reflection takes place and very little transmission takes place there. The intensity reflection coefficient alpha is the ratio IR over I, where IR is the reflected intensity and I is the incident intensity. Z1 and Z2 are the specific acoustic impedances of the two media. So alpha is equal to IR over I. So we can say IR over I, which is equal to Z2 minus Z1 all squared divided by Z2 plus Z1 all squared. So this will tell you the amount that is going to be reflected and the amount that's going to be transmitted, because you subtract from 1 if you, using a fraction. For example, a boundary between fat and muscle would give 1% reflection. That is, you look at, so that is fat and muscle. So there is fat here, and then that's muscle. So your Z1 would be 1.3 times 10 power 6. Z2 would be 1.70 times 10 power 6, and apply that in the equation. So 1.70 times 10 power 6 minus 1.3 times 10 power 6 all squared divided by Z2 plus Z1 all squared again. Then you find your value of alpha. So the alpha comes as a fraction. If you multiply by 100, you're going to get it as a percentage. So it will tell you the amount that is going to be reflected. So remember we said that the greater the difference between the two specific acoustic impedances, the more the reflection that will take place. So since we have got fat and muscle that give a reflection of 1%, while between fat and air, look at fat and air, 429 versus 1.3 times 10 power 6. So there's going to be much reflection. No ultrasound will penetrate the skin in that case. So which means if you want to get images from the body, there is virtually no way that you can do it if you just have air and fat. So we need what is called a coupling medium. So a coupling medium in this case would be a gel. A coupling gel is used between the transducer and the skin. so that we increase the transmission and reduce the reflection. So that is why when someone undergoes ultrasound, they need to be anointed with this coupling gel before they switch on the transducer. So I'm going to end the video here. That is on just specific acoustic impedances, and as well as the intensity reflection coefficient. Then we are going to look at attenuation of ultrasound and X-rays in the next video. Signing out.